can see remotely. So if anybody is against being recorded, let me know. You have the right to remain silent. Right? No, but really, no, jokes apart. If you're not comfortable being that the talk is being recorded, please let me know. Is that okay with you, Esteban?
If I'm allowed to use Photoshop afterwards.
Okay, sure. And you can sing. Esteban knows more Brazilian music than I do. So if you want to sing, we can make a CD afterwards.
We'll
also.
do that.
And another thing I wanted to say, so really, if you're not comfortable, just let me know, okay, for any reason. Or else we record, because then we have like a database of talks and people can remotely access, see it afterwards, and so on. Another thing is that I want to quickly say is we're going to leave to lunch right after the second talk, Oliver's talk. And there's a very nice place nearby, IMPA, which a little bit after noon or 1:15 noon, it starts getting crowded. So let's try to, after we finish the talk, of course we won't have to run, but we go to the bus and it's just like 5 minutes on the bus down the hill and we go to this place for lunch, which is called a Kilo restaurant. Some of you know what a Kilo restaurant is, but I have to explain. It's by the kilo. So it's a very nice restaurant. It's very efficient. The food's very, so you get your dish, you put your food, you weigh the dish, right? And that's why it's a Kilo restaurant. If you you pay for it, for how much you're eating. And one thing one has to be aware is that there's very good actually Japanese food and other food. The Japanese food is more expensive. So if you want to eat Japanese food and salad, don't put your salad on the Japanese dish, or else you're going to pay more expensive for the salad. Okay, that's all that you really need to know for the lunch tutorial. So, if you eat Japanese, it's a separate dish from the other one, and it's a very good restaurant. We'll go there after Oliver's talk. So, welcome to everybody. It's really a pleasure to have this distinguished crowd with many friends. And let me go ahead and introduce Esteban's talk. I don't even need my glasses. The title is up here, right? Esteban will speak on hydrostatic model for atmospheric convection. So, Esteban, the microphone is all yours.
Oh, thank you. Thank you. And thank you for Andre, Paul, Roberto, the organizers. It's always wonderful to be here. So how many of the minutes are for Sam and how many for the talk? It's
up to you.
Okay.
You're the DJ.
So the title reflects the hydrostatic model for atmospheric convection reflects what the idea was when I sent the abstract, but it's going to be more about the meridional extent of the tropics, which is something some of you heard. I mean, the first time I spoke about this was 3 years ago, I think, in this same room or another room, but here in IMPA. So it's hopefully, so things have been going on in this topic. So this is work with Paul, sitting here. And let me tell you what the whole thing is about. So some of you may know, some of you may not be aware that our atmosphere, or rather the troposphere, has the shape of a Mexican hat. Yeah? That the troposphere where we live, right, which is here in the tropics, is about 16 kilometers high. That will be this height here. Yeah? If you go to the high latitudes in both the southern and northern hemisphere, yeah, it becomes about 9 kilometers high. Yeah? So this is the interface between the troposphere and the stratosphere is called the tropopause up there. Yeah? And it has almost this continuity at 30 degrees. Yeah? North and south. Yeah? So part of this talk, or much of this talk, will to give you a possible explanation, yeah, that Paul and I came up with of why so. Why this sharp discontinuity and why at 30 degrees? Yeah? But what is, other than explanation, what is underneath the tip of the hat, yeah, are these convective cells, big convective cells, yeah, which are called the Hadley cells, that have much to do with the global climate of the Earth, right? So the air goes up in the middle, in this convective cell. As it goes up, it's very moist, and it rains a lot. This is the area where it rains the most on Earth. Right? If you look at Earth from a satellite from outside, you will see a thin layer of clouds precisely in this area, in this area, yeah, which is called the intertropical conversion zone. Yeah? So that's a lot of rain there. Then this air that is up moves towards the high latitudes. Yeah? As it moves, because of the rotation of the Earth, it veers towards the east. Yeah? And so here, at more or less 30 degrees, you have these strong jets. Yeah? Those are the subtropical jets, which is a strong air movement towards the east. Then it comes down, but this air has been dried already, right? It rained all the water it had in there. When it comes down, it becomes even drier. Yeah? And that's why you find here all the deserts on Earth, or most of the deserts on Earth, right? The Sahara and the like. Yeah? Then the air comes back here towards the equator. As it does, it's going the opposite direction. Now it veers towards the west. Yeah? And these are the trade winds, right? That come, say, that brought Columbus from Europe to the Americas. Yeah? So you can see that this has much to do with the climate on Earth, right? Okay? So there you have a picture of that. You have the cells, the same story, right? The trades, yeah, going towards the west, yeah, and up there you have the opposite, the westerly winds. So one funny thing about these Hadley cells is that they end very sharply at 30 degrees, independent of in which season you are, right? There is a picture borrowed from some paper that shows how these are the 12 months of the year, yeah? And you can see the two Hadley cells, the summer and the northern Hadley cells, and the winter Hadley cell is much, much stronger. The one you see there is the winter Hadley cell. The other one is much weaker, right? The one in the summer, much smaller. But both of them end at 30 degrees, yeah? So which is quite strange. I mean, for any proposal of why it should end there, should be very solid reason that stops at 30 degrees no matter what, under very different circumstances. Yeah? So you can see that they are in these pictures throughout the months, that things change a lot, right? This winter here becomes a summer at the end, so it's much, much smaller, right? And yet, it's still ended at 30 degrees. And so here is this transparency is the theory, this theory in one transparency, and then there come a lot of more, validation and extra details of it. The theory is all in here. It has to do with the simple fact that people in climate studies often tend to forget, yeah? Which is the fact that the sun is up there during the day and not during the night, yeah? So first of all, why do people forget that? Yeah. Why do people studying the climate forget that? Well, you want to study the climate over a period of months or years or decades or even centuries, right? You don't want a high frequency there with a period of one day disturbing your calculations. That's one practical reason. A more fundamental reason is if you look at typical relaxation times, yeah, of radiative relaxation times of the atmosphere to external forcing, it's more than a day long. It's maybe, depending on how you compute it, it can be a week, 2 weeks long. Yeah? Yeah? So from that perspective, you can say, well, I can average over these variations over the daily cycle, yeah, because there's no time for the atmosphere to adjust to it anyway. Yeah? So that would be a justification. I will argue that it doesn't apply in this case, but still, that would be a justification of why you tend to forget it. Now, if you don't forget it, now, let's think about it for a second. You have a force. So first of all, I should say, I mean, not everybody here works on geophysical flows. So a little bit, I'm describing at the limit of the troposphere. What is the troposphere? Yeah? Troposphere is the area of the atmosphere that is relatively well mixed. Yeah, quite well mixed. It's almost at constant entropy because the atmosphere is warmed from below by the sun. The radiation from the sun goes mostly through the atmosphere, warms up the ground and the ocean, and then the atmosphere is warmed from below, right, by infrared radiation and many other processes. If you warm a fluid from below, you create instabilities, yeah, like these Hadley cells. So this creates this very well-mixed area, the troposphere. Yeah, above it, the stratosphere is not well-mixed at all. It's in stratus, so in layers. Yeah. So anyway, so we have the sun then, who is responsible for the existence of the troposphere, and the sun has a period of 1 day. Yeah. So if you have a medium like the atmosphere, and if that is being forced with a certain period, the medium will respond to leading order with waves of that period. Yeah? A medium that permits, allows for the existence of waves. So you will have waves with a period of 1 day. Yeah? Now, but the atmosphere is in a rotating planet. It's a rotating fluid. So you cannot have any frequency for your waves. If you are in a rotating fluid, your dispersion relation, the dispersion relates the frequency to the wave number, yeah, has a lower bound. So the frequency starts with a number f called the Coriolis parameter, yeah, which has to do with the rotation of the Earth. So all the frequency of the gravity waves on the atmosphere have a minimal number given by this f, which is twice the rate of rotation of the Earth, yeah, times the sine of the latitude. So this is 0 at the equator, and it's maximal, yeah, this frequency at the pole. Yeah? This is the reason for that is the Coriolis effect, yeah? But let's take this as a fact. Yeah? So now we have waves with this period, right? With this period, because these are the waves forced by the sun with the daily cycle. But these waves have to satisfy the dispersion relation if they're going to be free waves of the atmosphere. So then they have to be bigger than f, so they have to satisfy this, which means that the sine of alpha has to be smaller than 1/2. Which means that alpha, the latitude, has to be between 30 and minus 30. Yeah? Yeah? So that's Paul and my explanation of why these sharp limits, and I have to say a bit more, right? But this tells you that the waves forced by the diurnal cycle of the sun, yeah, are trapped between minus 30 and 30. Outside of that, they decay exponentially. Yeah? So, okay, so waves. And what would do, so how do the waves, yeah, relate to the shape of the atmosphere? Well, then we have to, the atmosphere is a complex thing, and I don't really know the answer, but I have a few components of the answer. Alan, yes?
I thought the sun's radiation was trapped quite high up in the atmosphere.
What do you mean by that?
That the solar radiation
yes.
actually to create waves,
Yes.
on sort of like internal waves or something like that, was trapped quite high up. In fact, I thought when they measured tidal waves, one of the paradoxes is that actually the tidal, the atmosphere's tide at Earth's level is semi-diurnal.
That's right. So I'm going to discuss that a little bit. So because we're going to describe here are not the tides. The tides are global waves, right? I'm going to describe here shorter waves. The tides cover the full planet. Yeah, I'm going to talk of waves of a wavelength of about 1,000 kilometers. That comes later. But there's a full discussion going on for decades now of why this bidiurnal component of the tides. I'll go into that later. But so these are going to be different waves associated with the storms. Yeah. So these waves, particularly one thing I would like to show you, I think is coming next. Oh, okay, let me go into that. So I would like to relate these waves to somehow convective activity to storms, yeah? And the storms are going to be the big mixers, yeah, of the atmosphere, yeah? So the idea is these waves are trapped between minus 30 and 30. You have lots of storm activity therefore in there. That creates this taller atmosphere, troposphere between minus 30 and 30, yeah? So going to that. So if you're talking about storms, you need to somehow quantify at what speed these storms move. Yeah? So let's take it, just to validate whether this theory makes any sense as compared to observations, a typical speed for the movement of storms. Yeah? So it's a baroclinic, because it's called a moist baroclinic speed of the atmosphere, and that's a number in the order of, say, 15 meters per second. Yeah? If you take the speed and take the frequency of the period of 1 day, you get a wavelength. Yeah? The wavelength is about 1,000 kilometers. Yeah? So that's answering your question, but addressing part of your question, Alan. Yeah, 1,000 kilometers. So, and 1,000 kilometers is more or less, yeah, the distance between storm systems in the tropics. Yeah? So it makes sense to think that these storms, yeah, are somehow associated with this daily wave activity. Yeah? At least it's not a contradiction in itself. There is also a small parameter that comes with this, which is essentially you measure this length of 1,000 kilometers with the full circumference of the Earth, yeah, and that gives you a small number, right? Which tells there is separation scale, so you can trap waves. If you're talking instead of tidal waves, those are not trapped; these are global waves. I'm talking about ways in which you can do a scale separation between the actual wave activity and the slow variation of the Coriolis parameter with latitude. Yeah. So let me see if this is true. Is it true, yeah, that that we have a strong daily signal in the waves in the tropics, meaning between minus 30 and 30 in this definition of the tropics, yeah, and not in the extratropics. Yeah. So for that, let's just look at the website Wunderground, so Weather Underground, and look for data of various cities, starting of course in La Ciudad Maravillosa, yeah, and see if you can see that simply by looking at what people record on airports. So first of all, if you look at the temperature in Rio, this is 2 weeks ago, yeah. Definitely the temperature is a daily signal, but that's not surprise. The temperature has a daily signal anywhere, right? I don't think even if you live in New York, you also notice that it's warmer at 3 p.m. than it is at 6 in the morning, right? So that's not a surprise. It's not an evidence of any wave. It can be just a direct response to the forcing. Yeah? The pressure has also a daily signal, but as Alan pointed out, we will see more of that in other slides of other cities. There is a bidiurnal signal there, and much of this pressure is associated with the tides, with the thermal tides of the atmosphere. The place where I think things are clearest are in the wind, and more so in the wind direction. That you can see a very clearly daily signal in the direction of the wind, right? Going essentially at what is that? Up. Where am I? Yeah. Switching by 180 degrees, so changing direction, between day and night. Yeah. Now, if you look at Rio and you look at that, you can say, well, you're actually looking at the sea breeze, which to a large degree is true. Yeah. The sea breeze is a response to the daily forcing, so it's not in contradiction with this. But let's look at a place very far from the coast, like Bogota. Yeah. Also very much in the tropics, and you can see, well, this is a full month of a couple of years ago, but it's the same story. You can see again the daily signal everywhere, and particularly you can see it in the wind as well, even though you are definitely far from the sea. Yeah. Instead, if you look at Chicago, for instance, a place very far from, so certainly above 30 degrees, you don't observe that anymore. Yeah. And there is still, of course, a daily signal in the temperature, responding to just the direct forcing. In the pressure, you don't see it at all. And in the wind, you don't see it at all. You see a rather flat thing. And what you observe is that this tends to change over a period of a week or so. Yeah? You will observe that because in the extratropics, what you have is weather systems, storm systems, that come and last for a week or so and then change. Yeah? So a very non-daily thing. Same in New York, exactly the same story. Yeah? Yeah. So there is evidence then in just looking at the simplest data that the weather in the tropics is diurnal and the weather in the extratropics is not. Yeah? Take for instance Africa. Africa is a nice continent that has the nice property for our theory that is located almost precisely between minus 30 and 30. So it's a tropical place per excellence. And if you look at this picture of the winds, you do observe that there are weather systems or storm systems in areas that are about 1,000 kilometers in radius. Yeah? Roughly speaking. Also, this is part of a video that I'm not showing. And in the video, you see that changes over a day. Essentially, it has a period of 1 day. Yeah? While if you look at North America, yeah, you have a far more uniform picture. So there's no this 1,000 kilometers so clear displayed in there. And also, if you look at this picture over the day, essentially it doesn't change. It takes a few days for this to slowly evolve into a different pattern. Yeah? Same for Europe. Yeah? Yeah. So again, evidence that the tropics are very different from the extratropics in the existence of these waves. And you can see them temporally and spatially. Yeah? So now let's move to some theory. Yeah. And how can you, let's try to validate this theory. Right now, the theory is the Hadley cells are there because of this diurnal forcing. Let's see if you can build a simple model where you can see that happening. Yeah? And today you see two approaches, and hopefully next time in Rio, hopefully very soon, yeah, you'll see those two approaches coming together into a single one. Yeah? So the simplest model we can think of is that describes this circulation, is describe the troposphere as one layer of fluid, this one here, underlying a semi-infinite layer, the stratosphere and all the rest. Yeah? These two layers with constant density, and below the whole thing, a boundary layer, yeah? Yeah? Which is where all the surface winds take place. Yeah? So I think that's the simplest scenario where you can have some kind of circulation. You can have wind moving towards the high latitudes in the troposphere and coming back in the boundary layer. Yeah? Okay? And that's that. So one little thing, one requirement of any model is you have these opposite winds, right? Winds going in one direction meridionally in the upper layers and the other in the lower layers, and also the more important, the zonal winds, the winds in the east-west direction, change sign, right? They are westerlies here, and they are easterlies, the trade winds down there, yeah? So how does a model like this, can a model like this, the simplest one, account for that? Yeah, it's very simple, right? If you look at the pressure that is forcing these winds, the pressure is essentially, B stands for buoyancy, actually minus buoyancy. Think of it as density, yeah? So the pressure at the boundary layer is essentially all the weight of the atmosphere above it, which in this model is just the height of the atmosphere times the buoyancy, times the density. Yeah? While the pressure in the troposphere itself is an average of that. Yeah? So in the average you have the 1/2 of BH squared. Yeah? So there is a slight difference, yeah, between these two expressions. Even though it's the same buoyancy forcing both, yeah, the fact that one is average and the other isn't gives this little difference that accounts for this difference in the two formulas. The same buoyancy and height will have different pressure gradients in the troposphere and in the boundary layer. This will account with the winds going possibly in opposite directions. Yeah? Even though they are forced by the same differences. So of course that's true of the full stratified atmosphere as well, but it's good to see that it persists at the simplest level in this model. Yeah? So let's start with let's look now at this model in the simplest instance to see if you can create this kind of rotating cells. Let's forget the rotation of the Earth. Yeah? Let's prescribe the buoyancy B. Yeah? It's given some function that I will put in a second, at least here. This function, some function of latitude. So this is strongest in the equator and smallest in the, depending on what the sign of the density of buoyancy is, but it's when it was warmest in the equator and coldest in the poles. Yeah? And then you just have, in a steady situation, so let's maybe forget about the fact that we have a daily cycle at all. In a steady situation, what do you have? You have, in the boundary layer, you have a balance between the gradient of the force, the gradient of the pressure, and the damping of the winds. Yeah? Yeah, because the boundary layer is a thin layer, there is a lot of friction going on there. Yeah? Yeah? In many, many ways. Yeah? So, in the upper layer, in the troposphere, you also have the gradient of the force, but there's no damping, because you're too far away from the surface. Then you have conservation of volume. Fluid going towards the equator has to balance the fluid moving away from the equator in a steady state. Yeah? And that's it. And this system you can solve very easily, right? You start with B is given, so you solve for H in this equation. You replace it here and you have V. You replace it here and you have V. So lower cases will stand always for a lower layer for the boundary layer and a big upper case for the troposphere. Yeah? Good? And this is the picture, just solving those equations. This is the prescribed buoyancy, the prescribed density again. I mean, it's minus the buoyancy. Yeah? The corresponding height. Yeah? And the winds. And you see, in the boundary layer, if you look at the sign of the wind with respect to the equator at 0 degrees, it's negative to the north. So this is wind conversion towards the equator. Yeah? While in the troposphere, they are diverging from the equator. So you have this cell, a global cell in this case. There's no 30 degrees in this picture, right? It's a global cell of circulating air, just in this simple scenario. Yeah. Now let's add rotation. Yeah? So now I added the Coriolis parameter. That's almost the only change in the equations. You now have the Coriolis parameter now. Still looking at steady solutions. Now there is I had to add a tiny bit of nonlinearity for this to make sense. Because remember that the jets in the upper atmosphere are driven by winds moving from the equator towards the high latitudes, right? As they move, you carry angular momentum, yeah? And that creates the jets. So I need the carrying of momentum, which is nonlinear, yeah? So that's, you can see in this equation, yeah? The V, Uy, yeah? That's the carrying of angular momentum, or of carrying of zonal velocity by the meridional winds, yeah? So you need that. And so this is the nonlinearity. There is, this equation is, you see, it's the only nonlinear part of the system. And it has a funny property that is nonlinear up to a certain point, because this is something equated to 0. Either V is 0 or Uy is F. Yeah? Yeah? Allow me to look at these equations for a while. So there are two situations. One situation, V is 0. Yeah? If V is 0, we look at this equation, little v is 0 as well. Little v is 0, we'll look at this equation, U is 0 as well, the zonal speed in the boundary layer. So everything so far is, everything is 0, which is a nice property of solutions. Yeah. Now, that stops there, right? Once all of that is 0, I need, I'm sorry, and that continues like that. Everything is 0. All the velocities are 0 in that solution. Yeah. And that leaves me with, what does it leave me with? I'm sorry, U was 0, so this term has to be 0. But if BH is 0, the square root of BH cannot be 0. Yeah. So therefore, there will be a zonal speed in the upper atmosphere. Yeah. That's one solution. The other solution has the Uy equals F. That's the transporting of angular momentum. Yeah. And then, well, you can carry the full solution. Let me just show the result of solving this. So at some point you have to switch between these two solutions. Yeah? One will correspond to the tropics, the other one to the extratropics. Let me show a solution like that. This is it. Yeah. So there you have it. So you have again this cell now is the same as before if you look at the middle. Yeah. But it's located between some latitude and minus that latitude. Yeah. Outside of there's no speed, no meridional speed. You have these jets, yeah, in the zonal velocity at that point where the Hadley cells ended, yeah, and you have also the trade winds in the lower layer in the troposphere, yeah. So what does this tell you? That this simplest model goes a long way into reproducing the picture of the circulation, the tropical circulation, with one caveat, right? And that is that where is this point? Well, that's completely up to you, yeah? Because you plug in a forcing, B, you plug in which height you would like in the equator, yeah? And out of that comes this point where V touches 0. It's completely arbitrary, yeah? There's another caveat, which is, this is not the only solution. Another solution is extend the extratropical solution everywhere, have velocity 0 everywhere. And in fact, that's a stable solution, yeah? Yeah? So the idea will be when you bring in the unsteady forcing, you should first somehow make this the only robust solution. Secondly, they should decide where the boundary will be at 30 degrees. Yeah? For that you will need, but you will not see it in this talk, to solve the fully nonlinear version of this system. Yeah? And that's left for next time in Rio. Yeah? Instead, let me consider a simpler model. Yeah. The simple model, let me just look at, now let me look at so far I have included there was no day in any of the models. No diurnal cycle. Now let's bring in the diurnal cycle, let's simplify the rest. Let's make the model just one layer. Let's forget about the boundary layer altogether for this particular one. Yeah? Let's make everything linear. So what I have here is just linear shallow waters with the Coriolis parameter. That depends on latitude, and I'm forcing that, yeah, with the forcing with a certain period W. Yeah? And you do the equations, and you find out that the whole thing ends giving you an equation like this, which is very much like the area equation. It switches from waves to decay. So it's from hyperbolic domain to elliptic domain, depending on how the frequency relates to the Coriolis parameter. Yeah? So again, you have trap waves. Yeah? And if F happens to be, whatever F is equal to omega, which is 30 degrees for the diurnal forcing, you will switch between waves and decay. Yeah? And if you look at the answer, okay, so you impose a forcing now, a periodic forcing with a period of 1 day, and for instance, during the equinox, when the forcing is exactly at the equator, this is the picture you see. Yeah? Here you have the forcing, and the answer, in this case, is represented in perturbation of the height, but it's in all the variables, is trapped between minus 30 and 30. Yeah? And again, you see here about 7 waves. Yeah? That corresponds to the fact that this 1,000 kilometers wavelength of the right value, you pick the right value of epsilon for, yeah? And these are the other variables, the oral trap. In fact, you have intensification of the velocities at 30 degrees. Now, if you tend to the solstice, so you are in the middle of the summer in one hemisphere, winter in the other, the forcing is very different. Yeah? But the answer is very much the same trap waves between minus 30 and 30. Yeah? So this gives you a certain feeling of robustness for this trapping in summer and winter. Now, if you forget epsilon, now you look at waves but that move much faster. They move at the barotropic speed of the waves, the full atmosphere moving together. Then you have the thermal tides that Alan was asking about. Yeah? And this is completely different. These are not trap waves. The forcing is the same. Yeah? But the answer now is a global wave that covers the full atmosphere. And here, in this simple linear model, the answer will be diurnal. So this model does not explain the bidiurnal nature of the barotropic tides. Now, if you switch to an hypothetical planet that is rotating at one speed, but in which the sun is rotating at a different speed, yeah? So you don't have 30 degrees as the turning point, but some other latitude that you pick up because in the computer you can go before Copernicus and move around the Earth, yeah? In particular, for this experiment, we picked the turning point to be 60 degrees, and indeed, you see this wave trapping at 30 degrees. At 60 degrees. Yeah? So, yeah, the same for everything. Now, so far these are waves. Yeah? So what have we seen? That in steady scenarios, with a simple two-layer model, you can reproduce cells, but there's some freedom in where you put the cells. In the linear one-layer case, yeah, you have waves that are trapped exactly where you want them to be trapped. Now, we need to transform these waves into an actual profile. Yeah? So we need some rectification mechanism, and the simplest one will be nonlinearity. Yeah? So if you have a nonlinear system, yeah, and now have waves in it, the waves will break, and somehow out of that a new mean will emerge. Yeah? So we took, and this is still one layer, shallow waters, nonlinear. We did a little game that there's no time to play with it now, but you would like the breaking waves not to conserve mass, because you would like the breaking waves to entrain more air from the stratosphere. Yeah? So you would like waves that when they break, they conserve energy and increase the mass. And this is a little toy we had with Paul some years ago. And this is the simple scenario of the Burger's equation, where you switch from conserving mass to conserving energy and increasing the mass. You can do the same for the shallow waters, and you have an equation that instead of conserving mass, conserves energy at shocks. And then you simulate that with the daily forcing, and you find waves trapped between minus 30 and 30, and when you look at the height, at the various seasons, you have certainly a difference between the seasons, but they all end at 30 degrees. Yeah? So this sort of works that gives you these cells. So the next job for us will be to do essentially the same thing, but now with a two-layer model to see the emerging out of this, the circulation between minus 30 and 30. And that's it. So to summarize, the diurnal cycle that is very often forgotten in theoretical studies, yeah, although not by people in this audience, yeah, the diurnal cycle is, we believe, is a big player, in fact, one of the biggest players in atmospheric dynamics, creating the full meridional structure of the atmosphere. Yeah? The way this will go is by trapping the diurnal waves between minus 30 and 30. And also that you can do simple applied math in this problem. So there is a belief in recent years in atmospheric science that you need full GCMs to do anything realistic. Yeah? So full complicated models that capture every detail of every parameterization. But in fact, there is still place for doing very, very simple physical theories, simplified theories, that are, we think, to a large, very illuminating of what is going on, yeah, as to, I mean, in big phenomena. And that's about it. So we have minutes either for questions or for samba, whichever you choose.